Properties of sound waves. First, sound can be reflected. When you clap your hands, the sound wave will travel forward. When it meets an obstacle, for example, a wall, the wave will be reflected back towards the person and he will hear an echo. Let the distance between the man and the wall be d. The time interval during which the echo is heard is t, and v is the speed of the sound in air. Then we have an equation: total distance traveled equal to speed times time. We have 2d equal to vt. Hence, the echo method can be used to measure distance. D equal to vt over 2, or we can use the echo method to find the speed of the sound wave. V equal to 2d over t. Next, sound can also be reflected, due to the change in medium. Let's revise how light is reflected. When light travels from air to water, it will bend towards the normal, as shown in the diagram. From the equation, psi theta A over psi theta W equal to VA over VW, where VA, VW are the speed of the light wave in air and water, respectively. Because speed of light in air, VA, is larger than the speed of light in water, therefore we have theta A will be larger than theta W. That's why the light wave will bend towards the normal when it travels from air to water. However, for the case of sound wave, when sound wave travel from air to water, it will bend away from normal, as shown in the diagram. Why? From the equation, psi theta A over psi theta W equal to VA over VW, where VA and VW are the speed of the sound wave in air and water, respectively. Since the speed of sound wave in air is smaller than the speed of sound wave in water, therefore theta A will be smaller than theta W. That's why when sound wave travel from air to water, it will bend away from normal. Let's see how sound wave can be reflected due to the change in air temperature. In figure A, in the daytime, the air temperatures drops when the altitude increases. At higher altitudes, the air temperatures decreases. That means the speed of the sound wave will also decreases. When someone speaks, the sound wave will travel in the directions as shown. The wave will reflect upward. However, in figure B, at the night time, the altitudes increases, the air temperatures will increases. That means the speed of the sound wave will increase with altitude. In this case, when someone speaks, the sound wave will bend in the direction as shown. Sound can also deflect. In figure A, even though the man cannot see the radio directly, he can still hear the radio signal because the radio wave are deflected, passing through the corner towards the man. In figure B, even though listener A and B cannot see the speaker inside the room, they can still hear the sound wave produced by the speaker. Because the sound wave produced by the speaker after passing through the door gate, it will deflect. Therefore, both A, B, C can hear the sound wave played by the speaker. In daily life, deflection of sound wave is much more significant than that of light wave. Why? You have learned that for greater wavelength, the deflections is more significant. For sound wave, the wavelength is of the order of 1 meter. And for light wave, the wavelength is the order of 10 to the power negative 7 meter. Since the wavelength of sound wave is much larger than the wavelength of light wave, therefore sound wave shows much higher deflection than that of light wave. Also, the size of door opening D is almost 1 meter, which is of the order of the wavelength of sound wave. Therefore, sound can be deflected in a much more extent when passing through the doorway. However, the wavelength of light wave is much smaller than that of the width of the door. Therefore, light cannot show deflection. The interference of sound wave. Connect two loudspeakers 1, 2 to the same signal generator. When only one loudspeaker is turned on, the sound intensity level along the line X is very constant. However, when both loudspeakers are turned on, alternate loud and soft sounds are heard along XY. The loud sound is represented by L and the soft sound is represented by S. The reasons are that the sound waves produced by loudspeaker 1 and 2 add together. If they add together constructively, then a loud sound will be received. However, when the sound wave from 1 and 2 adds together destructively, then a soft sound is heard. There's a question. Where does the energy at the position of soft sound go? In fact, the energies at the positions of soft sounds go to the positions of constructive interference. That is, go to the positions of loud sound. Therefore, the law of conservation of energy is still true. For observable interference effect along XY, the separation between the loudspeakers D should be greater than the wavelength of the sound wave propagated lambda. Do you know why? For interference effect with first order maximum, the first loud sound is of first order m equal to 1. We have the path difference d2 minus d1 equal to 1 lambda. By geometry, we see that d2 minus d1 must be smaller than d. From this, we see that lambda must be smaller than d, or d must be larger than lambda in order to have first order maximum to be observed. As a conclusion, for observable interference effects along xy, that means we have at least first order maximum. The conditions is the separations between the loudspeaker must be larger than the wavelength of the sound wave. By connecting a microphone to a CRO, we can use the microphone and the CRO to show interference effect due to sound wave. When only one loudspeaker is switched on, the microphone detects the sound wave, and the CRO screen will show the sound wave in the form like this one. When both loudspeakers are switched on and the microphone is put at the positions with constructive interference on the CRO screen, we will show a graph like this one, which shows constructive interference, and the amplitude is about double. However, when the microphone is now put at the positions of destructive interference, and on the CRO screen, we will see a graph of the signal something like this one. Even for destructive interference, the resultant wave shown on the CRO screen is not zero, but has a minimum amplitude. There are two reasons. First, there are sound waves from the background, we call background sound wave. Second, the wave reaching from the loudspeaker to the microphones have slightly different amplitude. Therefore, they cannot cancel exactly.